Let's come to problem number 4, which is our last problem concerning equilibrium conditions and free body diagram. Therefore, it is a more developed problem where we have to include many equilibrium conditions, equilibrium of forces, equilibrium of moments, and so on. And we also want to state a problem which has some relevance to the reality. What is the problem like? We have a so-called railway crane we want to investigate. This railway crane here consists of different parts. First of all, we have the crane here itself, which is standing on the railways in the points A and B. And the problem statement says that in these 2 points A and B, only vertical forces can be transferred. So we have to include, if we make our free body diagrams, only the forces in, using this coordinate direction, in y direction, and no forces acting in horizontal, that means in x directions, at the points A and B. This part of the crane has the mass m1, and due to the acceleration of gravity, of course, there is a weight force caused by this m1 in negative y direction, in the same direction as this g is acting. Then we have in this crane the arm of the crane, which is mounted here in the point D and has a length of LA, so the length of the arm is LA, and we assume that this crane has a homogeneous mass distribution, so that the center of gravity of the arm is just in the middle of the arm. So the distance between this mounting point D, which is more or less a pinned bearing, to the center of gravity S3 would be LA over 2. Then there is a certain weight mounted on the arm's crane. Here in the hook H there is a bundle of pipes. And this bundle of pipes should have a mass mr. So there is once again a weight force mr times g, which is acting downwards. So in total we have so far this weight of the crane, the weight of the arm with the mass m3, and the load on the crane, which is mounted on the hook. Yeah, and what would happen right now if we have such a situation that here is some weight force acting and here is some weight force acting? Of course, these masses and these weight forces could cause that the crane doesn't stay stable on the ground, but that somehow it rotates in this direction, which would be a negative z direction. To prevent this rotation, we have a counterweight applied to the crane, and this counterweight then is acting in this situation, so it leads to a positive moment balancing the moment of the loads, and the distance between the center of gravity S2 of the counterweight and the center of the crane S1 is declared by B. So far to the system and the different parts in the system. What is perhaps necessary for us to know is the working angle of this crane. It might be horizontal. This is one extremal position. So the angle L, the angle gamma, which is the inclination angle, would be 0. Or it might be also vertical. So the inclination angle would be 90 degrees or pi over 2. So this is the working area of the crane. And yeah, then we can look at the given variables. We have first of all the mass of the crane itself is m1, which is 3 times m. Then we have the mass of the counterweight m2, which is not related to m. We somehow have to define it in our problem. We have the mass m3, which is the mass of the arm of the crane, which is 2 times m. And we have the mass of the load, which is mr, once again not related to this small m, but can be a variable mass. And concerning the geometry, we know the distance of the two centers for the crane and the counterweight, which is B equals 3/2 times A. A itself is the distance between the center of the crane and the point B and the point A respectively. So the width of the rails would be 2 times A. We know the distance between the point D, which is the bearing of the arm, and the center, which is C, is equal to 1/2 times A. The length of the arm LA is equal to 6 times A. And as I already mentioned, this working angle of the crane's arm is between 0 and 90 degrees. So what do we have to calculate? First of all, we are asked to determine the forces Fa and Fb between the crane and the rails, depending on the working angle of the arm. For the following sub-questions, we assume that the necessary counterweight M2 has to be examined, and we have different possibilities for the counterweights, namely 2 times m, 4 times m, 13 times m, and 18 times m. So 4 different possible counterweights we can apply. And we can consider 2 different extremal positions. So what is the problem in this situation? First of all, if we have an extremal position, namely our arm is horizontal and we have a big weight, big load on the right hand side, then of course our counterweight has to have a certain amount. If this is too low, then we would have a turnover of our crane in this direction. So it would just rotate in a clockwise sense. If we have, on the other hand, a vertical position of the arm and our counterweight is too big, then of course we would have a turnover in positive direction, a positive rotation with respect to the z-axis, and we also want to prevent this. So there are two boundary conditions we have to consider. Sub-question number C says determine the minimal value for M2, thus that the loaded crane does not turn over during operation. Assume as the mass of pipes mr equals m. Yeah. Sub-question D asks us to determine the maximum value for M2, thus that the unloaded crane doesn't turn over during operation. And sub-question E asks us which counterweights we can apply safely so that the crane can be operated in both cases, with and without loads. So somehow we have to choose appropriate weights between 2m and 18m for the counterweight M2 to fulfill this condition asked in sub-question E. Now I want you to start with sub-question A to make the free body diagram of our system and state the relevant equilibrium conditions to calculate the forces between the crane and the rails in the contact points A and B, so the unknown forces Fa and Fb. And once again, for you as a hint, in these 2 points only vertical forces can be transferred. So take 10 minutes and then we will come back to the solution. Let's come to the solution of sub-question A. In this case, our crane mounted on the environment, and we simply make a free body diagram. We plug in all the forces, which are the bearing reactions in the points A and B, as well as the weight forces at their defined positions. The weight forces, let's look at the load here. The weight force of the load is mr times g in negative y direction, simply in the center of the load. The weight force of the arm of the crane is m3 times g, and it is in the center of the arm. We know that the length of the arm itself is LA, and the angle alpha, the angle gamma, is the angle of the working angle. So it is measured with respect to the horizontal, so this is the angle gamma. And that means that the horizontal distance of the end of the arm to the beginning of the arm is just LA times cosine of gamma. That means that, of course, the center has LA over 2 times cosine of gamma as distance from the mountings. And therefore the position of the weight, which is located in the center of gravity of the arm, is defined. Then we have, as already mentioned, in the center of the crane, m1 times g, which has the distance a from fay, from the contact point A, and as well a from the force fby, which is going through the point B. And this small b gives us the distance between the counterweight force and the weight force of the crane itself, which have to be included. Just to repeat, fay and fby are acting in normal direction, so they are only vertical forces. Of course, these forces must be acting upwards, because these are normal forces which prevent that the crane is moving downwards, so the forces are acting upwards. They are pressure forces from the rails to the crane, and of course the same forces could be applied downwards onto the rails. That's it for all the unknown forces. Of course, we could replace the masses m1 and m3 by this given m, or we could replace the distances LA and C and B by the distances A, but that is not necessary for the free body diagram. We can plug it into the equations later on. Okay, so far the free body diagram, and now we can set up the equilibrium conditions. And what we can do is to choose appropriate reference points, because let's look at the system. We only have forces acting in vertical direction, so the sum of forces in horizontal direction has to be 0, gives us no further information. We only have forces acting in vertical direction. So we can state some equilibrium of forces in vertical direction, and then we have given values this m1 times g and m3 times g, but unknowns m2 times g, mr times g, fa and fb. So 4 unknowns for only one equilibrium condition does not suit well. The other possibility would be to set up the equilibrium of moments with respect to either the point A or the point B, and then we are fine, because the other if you choose, for example, the point A as reference point, then of course FB has a lever arm, but FA can be neglected as the line of action intersects the reference point and we have no lever arm for the equilibrium of moments. That is what is done here in this solution. So the sum of all moments with respect to the point A has to be 0. And now we just have to apply all the forces and the linked lever arms to this equation. First of all, let me just enter here a positive sense of rotation for the moments. So that means if my point A is the reference point, then this m2 times g has a positive sense of rotation. And the distance here is b minus a. So this is b minus a, which is the relevant lever arm we have to consider. The weight force of the crane itself, m1 times g, has a distance of a with respect to the reference point, so a is the lever arm, and m1 times g uses or leads to this sense of rotation, so a negative sense of rotation, therefore a negative sign here, minus m1 times g times a. This force Fp we want to calculate, acting upwards, leads to a positive sense of rotation with respect to this reference point and has the lever arm of 2 times a. So plus Fby times 2 times a. The weight due to the arm of our crane, m3 times g, leads to once again a negative rotation, and now we have to be careful to calculate the lever arm. We have first of all the distance between the mounting and the center of the arm, which is LA over 2 times cosine of gamma. Then we have this distance c, and we have this distance a, and all three terms have to be summed up, which is then here the complete lever arm. And finally, for the load here at the end, it's more or less the same structure as for the arm itself. We just replace this LA over 2 by LA, which is then this LA times cosine alpha plus this C plus A, and then this is our complete lever arm. Yeah, and if we want to calculate then the force Fb, assuming that we know the weight of the load and assuming that we know the weight of the weight m2, the counterweight, then we can solve this equation for Fby and replace all the geometric relations. So m1 equals, for example, 3 times m, and m3 equals 2 times m, and LA equals 6 times a, and C equals a over 2, and so on. And if we all plug this in, then we get as a result g times this lengthy expression, which only depends on the mass m, which describes as the mass of the crane and the arm, the mass mr, which describes as the mass of the load, and this m2, which describes as the counterweight. Yeah, and that's it for sub-question A. Now for sub-question B, once again you are asked to work this out. In this case, to state the conditions for turning over to the left or to the right, or the other way around, the conditions so that the crane can work properly without turning over. In the same way, we can set up the equilibrium of moments with respect to the point B to calculate the force Fay. It's the same statement, or more or less the same statement as for the first condition. But we could of course also calculate the force Fay using the equilibrium of forces in vertical direction. But in this case, just to make the proof, we just calculate the equilibrium conditions, and the only thing we have to check is that we have new lever arms for the same forces. For example, if the point B is the point of reference, then we have as a lever arm for the counterweight this B plus A as lever arm for the counterweight. It is once again a positive moment which is induced by this counterweight. We have to consider the weight of the crane itself, which has a lever arm A and which leads to a positive moment. And we have to consider now the contact force in the point A, which has the lever arm of 2A and leads to a negative sense of rotation, therefore minus Fay times 2A. And for the rest of the forces, namely m3 times g and mr times g, they are very similar to the expressions for the equilibrium of moments with respect to A. The only thing which change is here we had plus A and here we have got minus A, which is just the distance between A and B to A. This is just the difference here. And then if we plug everything in, we can explicitly solve for Fay. That's it. So using the equilibrium of moments has the advantage that we do not have to state one equilibrium of forces where we have the two unknowns Fa and Fb. In this case, setting up the equilibrium with respect to A gives us only the equation depending on Fb, and setting the equilibrium of moment with respect to B gives us only an equation depending on Fay, and therefore we do not have to plug in one result of one subquestion into the other subquestion. Yeah, and now please use these results to calculate the turning over position, the turning over conditions for both relevant cases, which is subquestion B. So I think that is a good point to stop with the first tutorial. We have had many topics today concerning equilibrium conditions, and we will continue with problem number 4 in our next tutorial, which will be on Monday the 1st of November. If you have the time during the weekend to recapitulate what we were discussing today, that would be very good. As already mentioned, equilibrium conditions and free body diagrams are essential for that course of engineering mechanics. If you have any problems or concerns, please do not hesitate to write me an email. And right now I say thank you so much for watching, and I hope you have a great day.